In today's video, we're going to talk about a strange quantum effect that has been observed for the first time by scientists in 3 different experiments. It's called Pauli blocking, and it makes a dense quantum gas suddenly turn transparent. But before we get into that, make sure you hit the like button and subscribe to our channel for more amazing quantum content. And don't forget to turn on the notification bell so you never miss an episode. So, what is Pauli blocking and why is it so strange? To understand that, we need to go back to the basics of quantum mechanics. Quantum mechanics is the branch of physics that describes how matter and energy behave at the smallest scales, such as atoms and subatomic particles. One of the most fundamental concepts of quantum mechanics is that these tiny objects can act both as particles and waves at the same time. This means that they have both a definite position and a definite momentum, but also a spread-out probability distribution that tells us where they are most likely to be found. This probability distribution is called a wave function, and it can interfere with other wave functions in a way that creates constructive or destructive interference. Constructive interference is when 2 waves add up to form a bigger wave, while destructive interference is when 2 waves cancel each other out. Now, there are 2 types of particles in quantum mechanics: bosons and fermions. Bosons are particles that can occupy the same quantum state as other bosons, meaning that they can have the same position and momentum. Examples of bosons are photons, which are particles of light, and gluons, which are particles that bind quarks together. Fermions, on the other hand, are particles that cannot occupy the same quantum state as other fermions. This means that they cannot have the same position and momentum as other fermions. Examples of fermions are protons, neutrons and electrons, which make up all atoms. The reason why fermions cannot share quantum states is because of a rule called the Pauli exclusion principle, which was formulated by Austrian physicist Wolfgang Pauli in 1925. The Pauli exclusion principle states that no 2 identical fermions can occupy the same quantum state in a given system. This principle has profound implications for the structure and stability of matter. For instance, it explains why atoms have different energy levels for their electrons, and why electrons fill these levels from the lowest to the highest. It also explains why atoms form chemical bonds with other atoms, and why solids have different properties such as conductivity or magnetism. But what happens when you have a gas of fermions at very low temperatures and very high densities? Well, this is where things get really interesting. When you cool down a gas of fermions to near absolute zero, which is minus 273 degrees Celsius or minus 459 degrees Fahrenheit, you create a state of matter called a Fermi sea. A Fermi sea is when all the available quantum states for the fermions are filled up to a certain energy level called the Fermi energy. This means that all the fermions are packed so closely together that they cannot move or change states anymore. They are essentially frozen in place. But what if you try to disturb them? What if you try to kick some of them out of their positions by shining some light on them? Well, this is where Pauli blocking comes into play. Pauli blocking is when quantum interference effects prevent most of the dislodged fermions from escaping their original positions. How does this work? Well, when you shine light on a Fermi sea, you are trying to impart some momentum to the fermions by absorbing or scattering photons. However, because of the Pauli exclusion principle, there are no available quantum states for them to move into. They are blocked by other fermions. So what do? They do something very strange. They boomerang back to where they came from. They fly away briefly, but then they return to their original positions almost immediately. This means that they don't interact with the light at all. They don't absorb it or scatter it. They just let it pass through. This makes the Fermi sea transparent to light, which is a very counterintuitive and surprising phenomenon. You would expect that a dense gas of particles would block or reflect light, not let it through. But that's not what happens in the quantum world. This phenomenon, called the quantum boomerang effect, was predicted by theoretical physicists more than 60 years ago, but it was never observed experimentally until now. In 2021, 3 independent teams of scientists from different countries managed to confirm this effect using different atoms and different methods. The first team, from Germany and Israel, used a gas of lithium atoms trapped in a magnetic field and cooled down to a Bose-Einstein condensate, which is another state of matter where all the atoms act as one giant quantum wave. They then applied a short pulse of laser light to kick some of the atoms out of their locations and observed their movement with a camera. The second team, from New Zealand and Australia, used a gas of potassium atoms trapped in an optical lattice, which is a grid of laser beams that creates a periodic potential for the atoms. They then applied a magnetic field gradient to nudge some of the atoms out of their positions and measured their response with another laser beam. The third team, from the US and China, used a gas of strontium atoms trapped in an optical dipole trap, which is a focused laser beam that creates a potential well for the atoms. They then applied an electric field pulse to displace some of the atoms and detected their motion with another laser beam. All three teams found similar results. The atoms moved away from their original positions for a very short time, but then returned to them almost instantly. The light scattering off the gases was significantly lower when they were cold and dense enough to form a Fermi sea. This confirmed the existence of Pauli blocking and the quantum boomerang effect. This is a remarkable achievement for quantum physics and a testament to the power of human curiosity and ingenuity. By observing this strange quantum effect, we have gained new insights into the nature of matter and light at the smallest scales. We have also opened up new possibilities for future research and applications. For example, Pauli blocking could be used to manipulate quantum systems in novel ways, such as creating quantum switches or sensors that can be turned on or off by light. It could also help us understand other phenomena that involve quantum interference effects, such as superconductivity or quantum Hall effects. And who knows what else we might discover by exploring the weird and wonderful world of quantum phenomena. The sky is the limit. Or maybe not even that. Thank you for watching this video. I hope you enjoyed it and learned something new. If you did, please give it a thumbs up and share it with your friends. And don't forget to subscribe to our channel for more amazing quantum content. And leave a comment below if you have any questions or suggestions for future topics. Until next time, stay curious and keep exploring.